Okay, so welcome back. This is section 2. In the first section of this series of lectures, we talked about the setup of the endogenous growth model with human capital, and we set up the Bellman equation. So I discussed the objective function, which was just like what we saw in the neoclassical growth model. I talked about the constraints, which differed a little bit, as we can see in the Bellman equation itself. All right, consumption is now equal to, well, some other stuff. And the Bellman equation is no longer just a function of physical capital, but also human capital. Now, before we go any further with the calculus for this stuff, what I do want to say is when I was talking earlier in the first video about this stuff kind of being like firms investing in their people to go to work or go to school and get additional knowledge, right, to expand their human capital, to expand their knowledge base, that's sort of like a short run, medium run type investment decision, right? Same thing as you going, I think I want to get a PhD in economics, kind of like what I did. And that would be kind of like a short to medium run, right? It's not exactly 1 year, it's, more like 4 to 5 years, in my case, 6 years. Not that I was like a bad student or anything. It was more of just, well, my research took a while. But the stuff, though, with this is, or the idea behind that is short to medium run. But another way we can think about this is also sort of family planning, like a dynastic family thing where parents of, say, Generation T decide how much human capital they want to invest in their children, which would be Generation T plus 1, or time period T plus 1. So that's like a really long-run growth and development type scenario that we would be looking at, where we have basically planning that will go from one generation to the next. So parents will go, well, I've got a high school diploma, but, I really want my kids to get at least an undergraduate degree. Well, when that happens in this model, they would choose an HT plus 1 that is larger than HT because, well, their kids are getting, a BA or a BS, a bachelor's in something or other. Right, so it would be larger than HT, so they're investing in the human capital stock, but they're not doing it for them. They're not doing it for their own personal gain. They're doing it in a more altruistic way of trying to ensure that their children have a better life than what they did, right? And it can also just be they're seeing, okay, well, the parent goes, well, I've got a good enough job as is, right? Like, for example, my dad doesn't have a 4-year college degree, but he's a senior VP of a nice division at Gulfstream. And if any of you know Gulfstreams, there's really nice fancy corporate jets. That probably wouldn't happen today, right? I mean, he's got an excellent tech degree. He has excellent training. He was in the Marines for a while. So, like, he accumulated human capital, just not through formal schooling, not through formal training, right, in the sense of schooling. He got human capital more from, like, on-the-job training. But, when he had me, he's like, well, I'd kind of like my kid to, have, like, at least a 4-year degree. So when my father, well, not just my father and my mother had me, they decided, well, okay, yeah, Jeremy's going to get a college degree. And I got a college degree. And, well, then I just happened to sort of be the oddball in that group where it was like, college degree isn't enough. I want to learn more about economics. And, well, that's what happens when you're a giant nerd like me. They probably didn't foresee having anyone who's as much of a nerd as I am, but hey, it is what it is. But in this model, it's fully deterministic, so households go, okay, I would like my children to have X amount of schooling, and their children just get that much schooling, right? There's no oddball in that case. So it can either be a short run or a medium to long run sort of scenario. And I just kind of wanted to address that before we went any further. Now, as we go further, Let's see, how far are we in this timeline? Oh, okay, 4.5 minutes, excellent. So, what we get is we're gonna have to take 2 partial derivatives here. One with respect to capital, one with respect to human capital. So we'll do the physical capital one first. Remember, Physical capital is a state variable, so it's kt plus 1, because kt was chosen yesterday. So we do just like what we did with the neoclassical growth model, only here I'm going to skip a step. Instead of 1 over all this junk, right, because the derivative of the natural log of this junk is 1 over this junk, I'm just going to do 1 over ct, because all this is equal to ct. So it's just 1 over current consumption. Now, chain rule, because, chain rule, chain rule, chain rule. Isn't the chain rule great? And if you're a nerd like me, the chain rule is wonderful. I love it. So cool. But either way, you got to remember the chain rule. Derivative of the inside with respect to kt plus 1 is negative 1. So it's 1 over ct times negative 1 plus beta times the partial of v of kt plus 1 ht plus 1 with respect to kt plus 1, and we set that equal to 0. Cool. Right, aside from that ht plus 1 thing, nothing really looks all that different. So let's do the next derivative. Well, we did with capital, right? So here we're optimizing with respect to capital, but the next thing we have to do is optimize with respect to human capital. Because now we're differentiating between physical and human capital. So if we are going to be optimizing this with respect to physical and human capital, well, we've done it with respect to physical capital. We just need to do it with respect to human capital. So what do? Well, take the derivative of that Bellman equation. Now with respect to ht plus 1. And so we take 1 over all this crap, right, which just gives me 1 over ct. All right, now we got to look on the inside. The derivative of the inside with respect to ht plus 1. What is it? Well, kt plus 1 is negative 1, but we're also subtracting ht plus 1 here, right? So the derivative for that is also negative 1. Not bad. Plus beta times the partial of this thing, right? V of kt plus 1, ht plus 1, with respect to ht plus 1. We set that equal to 0. Right, and that's what we got. Just this stuff right here. So these are our 2 first order conditions. But remember, we have to figure out what this is, and we have to figure out what this is. Because if we look here, right, if we want to just update this guy 1 period, well, the time subscripts don't match. Right, but here the time subscripts do match. So these aren't exactly the same derivatives. So we have to take a derivative that will give us this and a derivative that will give us this. What is that? Well, I'll do it in purple. We take the derivative of this value function, or this Bellman equation. First with respect to physical capital. What does that give me? Well, again, it gives me 1 over ct, right? Because derivative of the outside, 1 over this junk, times the derivative of the inside. What's the derivative of the inside with respect to kt rather than kt plus 1? Well, let's see. We have to differentiate this production function now. So we get alpha times at times kt to the alpha minus 1 times ht to the 1 minus alpha. Right, so we got that part done. There's another kt that shows up. It's here. It's going to be plus 1. Now in the last model, right, we added not just 1, but we added 1 minus delta. But that was assuming that there was depreciation. Here, there is no depreciation of physical capital. Now when we update this 1 period, you get 1 over ct plus 1. Because all we're doing is just adding 1 to the subscripts, right? So we get 1 over ct plus 1 times the marginal product of capital, or the marginal product of physical capital, alpha times at plus 1 times kt plus 1 to the alpha minus 1 times ht plus 1 to the 1 minus alpha plus 1. That's what we get, right? So if this partial of the value function of kt plus 1, ht plus 1 with respect to kt plus 1 is equal to this right here, well, this and this are the same, right? Just like in the neoclassical growth model. So what I could do is I can actually just take this purple thing here and just plug it in here. So we will do that in just a moment. Before we do that, let's look at the derivative of this thing, well, I guess this thing, but with respect to ht, and then update that one period as well. Right, well, it's going to be the partial of this value function, kt, ht, with respect to ht. Right, well, remember, just like we had with this thing with respect to kt, instead of ht, we got 1 over ct times a bunch of stuff, right? Well, same thing holds here. You get 1 over ct times a bunch of stuff. But the stuff is now going to be different because I'm differentiating with respect to a different component of this production function. It's not alpha anymore, it's 1 minus alpha that becomes the leading coefficient. So it is 1 minus alpha times at times kt to the alpha times ht. 1 minus alpha minus 1 is just minus alpha. But there's another ht right here, so that's just going to be plus 1. Look at that. So I'll let you look at that for a moment, look at the differences and similarities between the two derivatives here. Actually, let me make this one a little bit more. There we go. It looks a little bit more like a 1 now. All right, so I'll let you take a look at that for just 1 second and kind of look at the differences and similarities. And maybe actually even push pause on this for a minute, or don't. It's no skin off my back. I'll actually take a minute to let you try to figure out, just for a second, what you think this is going to be updated 1 period. What I mean by that is try to give me that. God, while I did that, ooh, I think I need a minute to recover. I was smelling that ink or whatever that stuff is from that marker. God, it reeks. Ugh, it's terrible. Probably need a minute to like come down from that high. Jeez, it's worse than huffing glue. Anyways, so take a minute, try to figure out what you would get for that. Okay, let's see if you got what I got. We get 1 over ct plus 1 times 1 minus alpha times at plus 1 times kt plus 1 to the alpha times h t plus 1, the negative alpha plus 1. That's what I got. Double check, see if what you got is what I got. And because, again, there's really no way to tell if you are, as this is not done in real time, there's really no way to tell if what you're getting is equal to what I'm getting, at least for me to tell. Oh, excuse me. So I'm going to assume we all got it now. And now what I'm going to do is I'm going to plug these two things in up here. I can find my makeshift eraser. And hooray, I did. So, beta times 1 over ct plus 1, we're doing kt plus 1 first, multiplied by the marginal product of physical capital like that, and it's, well, still equal to 0. So that's what we get. Now, for human capital, I just take what's in blue here, put it right here. What do I get? Well, it's, again, 1 over ct plus 1 times 1 minus alpha times at plus 1 kt plus 1 to the alpha times h t plus 1 to the minus alpha, again, plus 1. And that is also equal to 0. So this is my marginal product of physical capital. Right. That tells me how much more output I will get for adding 1 additional unit of physical capital into the production function. But remember, the production function now has 2 inputs. So I've got another marginal product. This is the marginal product of human capital. This tells me how much more output I will get for adding 1 additional unit of human capital into the production function. So I want to know how much physical capital am I going to get, or how much more output will I get from 1 additional unit of physical capital. But then there's also going to be the question of how much more output do I get by adding 1 additional unit of human capital, not physical capital. So what that really gives me here are 2 different Euler equations. There's the Euler equation for physical capital and an Euler equation for human capital. Now you're probably going like, what the hell? I thought there was just 1 Euler equation. Well, there's 1 Euler equation in certain cases, and sometimes we get more than 1 Euler equation. Here we have more than 1 Euler equation, because there are multiple ways that we can either consume or save, right? So there's still the consumption axis, or the consumption dimension that we're looking at, but there's also, instead of just consumption and savings, where savings is physical capital that we get, now there's also human capital. So we now have to decide between consumption and human capital, as well as consumption and physical capital. Thus, we have 2 Euler equations, because we're determining how consumption is going to change with respect to these other variables, these other mechanisms. I almost said methods and then like stopped myself halfway. I don't know why I did that. These other mechanisms through which we can save. Because it's no longer just physical capital, but it's also human capital that we're investing in. So, with all that said, I'm going to erase this stuff on the bottom. Actually, you know what? F it. I'm going to erase all this stuff. Because I need the board space. And you've already got it in your notes, as do I. So what do we do here? Well, like I said, we rewrite the stuff. The way I'm going to rewrite this is I'm going to solve those first order conditions by just giving basically these two equations. Where do we go from here? There's my notes. Okay. So solving accordingly. I get 1 over CT equals beta times, and purple, this is with physical capital, I get this. So this is my Euler equation for physical capital. But there's another Euler equation that I'm interested in, and it's human capital. So that one gives me 1 over CT equals beta. That beta looks a little bit bigger. That works. Oh, not like a beta, less like a B. Beta times, well, 1 over CT plus 1 times 1 minus alpha times AT plus 1, KT plus 1 to the alpha times HT plus 1 to the negative alpha. That looks a little bit negative. Geez, maybe I can't. Maybe negative alpha plus 1. That's what I get. So I get these two Euler equations here. So really all I did was just rewrite the first order conditions. But this tells me that there's an evolution of consumption, but along not just a capital axis or capital dimension, but there's also one for human capital. So there's KT and HT now. So where do we go from here? Well, where we go is actually kind of neat. Because notice, well, there's actually a lot in these equations that are equal to each other. Right, we got a 1 over CT in both equations. We got a 1 over CT plus 1 in both equations, and we got a beta in both equations. So, I'm not going to use different colors anymore. I'm just going to, what the hell, doing different colors. Different colors are fun. So for this equation, what we would get is, if I multiplied both sides by CT plus 1, I'd get CT plus 1 over CT. But I need to divide both sides by beta. I get 1 over beta. And that's equal to the marginal product of physical capital plus 1. Like that. And I'll just do the exact same thing for the human capital Euler equation. All right, well, I get CT plus 1 over CT times, just this goes over here, times 1 over beta, and that equals the marginal product of human capital. It's a human capital. I'll start trying to write out physical capital. So it gives me that. Now the cool thing is, by this Euler equation, right, the left-hand side of the purple and the blue equations, right, that left-hand side are equal to each other. CT plus 1 over CT times 1 over beta. Those two guys are equal to each other. I'm just writing it out. It's color-coded. So we get that, right? Those two things are equal to each other. So if the left-hand sides of these two equations are equal to each other, well, that means the right-hand side of these two equations have to equal each other. So what it implies is, well, something that probably requires me to erase the board again and rewrite. I want to have a little bit more space. Because this is that one time where you're like, I need some space, I need more space. And it doesn't end with somebody drinking themselves to sleep every night for 3 months, crying over what they think should have been but never should have. Really dark, I know. So what it implies is the following. That the marginal product of physical capital in equilibrium is going to be equal to the marginal product of human capital. Right? Now, if you're wondering about what I did with that plus 1, well, I'll write it out just so you can see what I did. feel like it would be kind of not good if I didn't explain the step that I skipped, even though it's a minor one. So it really gives me this, right? But if I subtract 1 from both sides, right, so you can add anything you want to either of these, and the equation's still going to be the same, right? If you add 12 to this, you're going to add 12 to this, and well, it's still equal. So getting rid of that, I just get alpha times at plus 1 kt plus 1 to the alpha minus 1 times ht plus 1 to the 1 minus alpha, which is equal to my marginal product of human capital, 1 minus alpha times at plus 1 times kt plus 1 to the alpha times ht plus 1 to the minus alpha. All right, so that gives me this right here. So this means my marginal product of physical capital is equal to my marginal product of human capital. So in equilibrium, the amount of output that I gain by adding 1 more unit of physical capital is equal to the amount of output that I gain by adding 1 more unit of human capital. So basically, it means that on the margin, right, when I'm in equilibrium, right, when this model is in equilibrium, it says that, again, on the margin, the amount of output generated by 1 more unit, or adding 1 more unit of human or physical capital, right? So if output grows by, say, 2%, by adding 1 more unit of physical capital, if I were in equilibrium, then output would also grow by 2% if I added 1 more unit of human capital. So that's what the marginal products being equal to each other implies. Now, a little bit of algebra, a little bit of stuff to work out. I'm not going to go through all the algebra because, well, you will not be responsible for all the algebra on this stuff. I kind of think I've made you guys do enough algebra and solving these things out already. I don't need to make you do one more thing with algebra. All right, what we get is, I'll say, yeah. After lots of math, I get the following. I get that kt plus 1 ends up being equal to keep the colors a little different. Alpha. Actually, you know what? I'll even make this one different. So you know exactly what equations these guys are coming from. kt plus 1 is equal to alpha over one minus alpha times ht plus 1. Now, because this holds for all t, right, for all time periods. For every time period this holds, we could also say can really just sort of be done as, we can even think of it as just kt equals alpha over 1 minus alpha times ht plus, or ht. So it holds for all time periods. So it holds for t, t plus 1, t plus 2, t plus 3, t plus 4, all the way to infinity. If we are in equilibrium, then we get this. Well, what does that tell me? What does that actually say? Well, it means that because the marginal product of physical capital is equal to the marginal product of human capital in equilibrium, or at the optimum, right? Households, when they're optimizing, they will invest in physical and human capital up until the point where their marginal products are equal to each other. So if, say, the marginal product of physical capital is, we'll say, 0.03, and the marginal product of human capital is 0.05, well, we're not in equilibrium. We're not optimizing, right? What that's saying is that the return to human capital is much higher than the return to physical capital. So what do? Well, we invest a little bit more in human capital and a little bit less in physical capital. So as we do that, well, we will end up getting something like, both of them are equal to, let's say, 0.4. Right? But when we simplify everything down, and I mean, you can work through all this math if you want to. It's in the book. You don't have to do the math. But when you simplify everything down, you get this little relationship right here. Right, so let's talk about what the alpha and 1 minus alpha are. So I know I've talked about what alpha is like in the Solo model, right? It's capital's share of output. Well, again, here, actually capital's share of income. This 1 minus alpha human capital's share of income. No, it's dumb. There we go. Looks a little bit better. Marginally. So there's capital's share of income, human capitals, or physical capital, right? So put KT in parentheses there, and I'll put HT in parentheses here. See, the amount that it's contributing, right, the amount that human capital is contributing to income and the amount that physical capital is contributing to income right? Alpha 1 minus alpha, or that share of income really, when kt equals alpha over 1 minus alpha times ht, right? And if we want to get like alpha times kt, let that be equal to 1 minus alpha times ht, right? Oh. 1 minus alpha to the negative 1, alpha to the negative 1. Oops. Yeah. Right, well, what that says is that when those two things are equal, we're optimizing. So if I am investing in capital, now this isn't to say physical and human capital are equal to each other. Now there is a situation where they can be equal to each other, but that's not what happens in equilibrium, right? Like it's not, that's a unique case, but that isn't of all cases, right? Because they're being weighted by their shares of income. Well, 1 over their shares of income, really. Right, so they're being weighted by these. Now, if these two are equal to each other, so say if kt equals ht, then 1 minus alpha equals alpha, which implies alpha is equal to 1/2. But alpha doesn't have to equal 1/2, right? Alpha can be anywhere between 0 and 1. So think about what happens if alpha is closer to 0, right? Meaning capital's share of income is a little bit less than human capital's share of income. Which one do we invest in more? Right? Then think about what happens if human capital's share of income. So what I'll say is think about what happens when alpha is less than 1/2. Then think about what happens when alpha is larger than 1/2. Think about which one we would be investing more in each case. If alpha is less than 1/2, do we invest more in physical capital or do we invest more in human capital? If alpha is larger than 1/2, do we invest more in human capital or do we invest more in physical capital? So I'll let you kind of think about that to get sort of the idea of what we're sort of looking at, like what we're up against when we're deciding how we want to invest this stuff. So I'll let you think about that one on your own. And then the last thing I'm going to do, well, I'm going to skip section 6.4 on this, so the general equilibrium stuff, right? Because we really just write out the 2 Euler equations and then the 3 constraints. So with that, I mean, I'm not going to make you list out the general equilibrium on the exam, nor am I going to, even assign anything like that on the homework. So I wouldn't be too worried. I mean, I would read it over, understand it, look at what it says. But really, we're just adding one more equation into the mix. No big deal. So that will wrap up this video. So we are actually done with the math. This is the last general equilibrium model that you're going to be responsible for solving. There will be one more model that has a little bit of calculus in it, but it's very, very, very easy calculus. It's a lot easier than what we've been doing. And so I wouldn't worry about that too much. So this is the last time you'll actually be responsible for anything that requires any sort of calculus whatsoever. Therefore, I wrap up this video talking about the math. The next video will be a lecture discussing some of the intuition behind this model, because this is really where we can actually start to squeeze a lot of intuition out of this, right? So, the first two general equilibrium models we looked at, the neoclassical growth model and the endogenous growth model with perpetual growth, they had some interesting stuff, right? There's some interesting implications to that, but there wasn't really anything that was like super cool aside from explaining, neoclassical growth model, certain types of shocks, and then the endogenous growth model, human capital spillovers. But here, we can get a little bit more of a concrete example. So there's going to be about a 30-minute lecture on some of the intuition behind this particular model. And once that's done, then this will wrap up everything for growth and development. And we will then move on to business cycles. So last thing that I'll say for this, expect one more video by the end of the week. And after that video, we'll start business cycles. Now, I will be assigning the exam by next Friday. Might even be next Thursday, honestly. You'll have until that following Tuesday to complete the exam. So you'll have more than enough time to work on it. And I am also giving you 2 weeks worth of heads up before the exam is due. And I just happen to be assigning it a couple days before, just to give you some extra time. You can work in groups. I have no problem with you working in groups, but the work you submit must be your own. So don't submit an exam with like 5 names on it. As helpful as that is for me to grade, that takes way less time for me to grade. It doesn't show me that you know what you're doing. I need to see that you know what you're doing. So with that said, that will conclude this video. Be on the lookout in the next couple of days for the video that really discusses a lot of the intuition behind this model. And we can sort of think of everything that we have done culminating in this particular model where we can actually squeeze out a lot of intuition from this model. So that will conclude this video. Thanks for watching, and I will see you next time on I sneeze, macroeconomics on NyQuil.